topic of today's video is going to be balancing full-blown redox reaction equations using the half reaction method. Now keep in mind, what we've learned up to this point is what a redox reaction is. We know that a redox reaction is composed of two half reactions, one resulting in oxidation, one resulting in reduction. Now, we also know how to take an individual half reaction and balance it according to the rules that I gave you in either acid or base. So what we want to do today is to take all of this information and combine it back together so that we can see how to balance a full-blown redox reaction that contains both types of half reactions. In other words, if we have a full redox reaction, we know that we have to have both oxidation and reduction occurring together, which means that we have to have both half reactions represented. All right, so here's a simple example of a full-blown redox reaction equation. This one involves oxalate ion in solution reacting with permanganate ion in aqueous solution to give us manganese 2+ ion in solution in carbon dioxide gas. Now the first thing that we have to do in a case like this, if we recognize that both half reactions are present, is we have to identify the individual half reactions and separate them out. Okay, at this point we don't need to know which one is oxidation and which one's reduction. We'll figure that out later. But how I do this is I look for like things on either side of the arrow. So you can see here in this particular case, the C2O4 2- has the same elements involved to a certain degree as the carbon dioxide. So that tells me that those are two like things. So those things probably are going to account for at least part of one of my half reactions. The other half reaction has to involve the permanganate ion going to the manganese, because this is the only thing that has the manganese in common. All right, so those have to be by default my two half reactions. So the first thing you want to make sure that you're adept at doing is making sure that you can identify the two half reactions in the unbalanced reaction equation. And that's exactly what I've done here. So here's my first half reaction. This has the reactants in the product that I single underlined. And then here's the second half reaction involving the manganese that has the double underlines under it. One of these corresponds to oxidation, one corresponds to reduction, and we'll find out which later. So once we've identified and separated out the two half reactions, the next thing that we have to do is to individually balance each half reaction. So let's do that. We know how to do that from class. All right, so C2O4, carbon is the first place I go. It's the non-hydrogen oxygen element. 2 carbons on the left, I need 2 on the right. I'm going to use my coefficient here in front to do that. We go to oxygens next. All right, we see that we have 4 oxygens here. 2 times 2 is 4. So our oxygens look like they're balanced out, so I don't need to add any waters to either side here. How about hydrogens? Well, it doesn't look like I have any hydrogens in this particular half reaction to worry about as well, because I don't have any waters. So the last thing that I have to do is to balance the charge on this half reaction. All right, so I've got a 2- on the left. I've got a 0 charge on the right because carbon dioxide is molecular and exists as a gas. So now what I need to do is add my electrons to the more positive side. All right? So I need to add enough electrons to the right-hand side to compensate for the 2- that I have on the left. So that's going to be 2 electrons. All right, so let's look at the second half reaction. Go through the same set of steps. All right, manganese we look at first. I've got 1 manganese on the left, 1 manganese on the right. Now I have 4 oxygens on the left because we do oxygen next. So I need to introduce 4 on the right. So we're going to do that by introducing 4 water molecules. All right, water, it's molecular, it's a liquid. No charge on that. Now the next thing that I have to do is go to the hydrogens. I have no hydrogens on the left, but it looks like I've got 2 times 4 or 8 hydrogens on the right. So I need to introduce 8 hydrogen ions to compensate. Okay, so my hydrogens ought to be balanced out left and right. Now the last thing that we have to do is look at the electrons, or rather look at the total charges here. So let's see what my total charge on the left is. It's 8+ and 1-, so that should be what, a 7+? And what have I got on the other side. It looks like I've got a total charge of 2 plus again because the water is neutral. All right, so the rule says now that I have to add electrons to the more positive side to make the charge equal to the less positive side. So it looks like here I need to add 5 electrons to the left-hand side to make the 7 plus equal to the 2 plus that I have over on the right. So now that I've got the 2 balanced half reactions, the next thing that I have to do is to put everything back together. So what that means is I have to add these half reactions together. But there's one other thing that I have to check on before I do that. And that is, when I have a redox reaction, I need to have the number of electrons be the same on both sides of the arrow. In other words, I can't just generate electrons, or I can't just lose electrons. All right? But we don't have that situation here. We see that in the reduction side, I need 5 electrons to satisfy this requirement, but I've only got 2 electrons being given up here on the oxidation side, right? So what I need to do here is I need to be able to compensate so that the number of electrons end up being the same on both sides of the arrow in both half reactions. So in this case, I'm going to just do a little bit of multiplication. So I'm going to take this whole half reaction here, and I'm going to multiply it through by 5. All right, that'll give me 10 electrons. Now if I want to also do the same thing down here, I can multiply this half reaction by 2 also to give me 10 electrons. Now what's going to happen when I distribute all this through is that my 10 electrons required here will actually be provided by the 10 electrons available to me from the oxidation step. All right, so that's sort of the last thing that we have to do to make everything balance out. All right, so let's rewrite everything. Now what I'm going to do is I'm going to go ahead and add these together while I distribute. So keep me honest here and make sure I do it right. So I've got to distribute the 5 all the way through, so that's going to be 5 C2O4 2 minuses. All right? Then I have nothing else here. But now I have to come downstairs to my other reactants. And it looks like now I have to have the 2 distributing through times the permanganate. So I need 2 permanganates. All right? I need 2 times 8, which is 16 hydrogen ions. And I also end up with my 10 electrons. Now let's go over to the reactant side. Again, I'm going to distribute through by my 5. Twice 5 is 10, so that's 10 carbon dioxides. And I'm going to get 2 times 5, which is 10 electrons. All right, now we got to come downstairs. 2 times the permanganate, that's 2 permanganate, or sorry, manganese 2 ions. And 2 times 4, which is 8 waters. All right, so now what I want to do is I want to simplify it. See if there's anything that I can get rid of on both sides of the equation here. So the one thing that I see that's fairly obvious here is that I can get rid of the electrons here, and I can get rid of the electrons here. The other thing I normally look for is either hydrogen ion or water, and it looks like I don't have any hydrogen ions I can cancel out on left and right, and it looks like I also don't have any waters that I can cancel out here. So it looks like in this particular case, what I've now got is a balanced overall redox reaction. Okay, so just in summary, what we've done here is we've taken the original unbalanced redox reaction, I've broken it up into 2 half reactions, all right? Then what I've done is I've individually balanced each half reaction, and then I can identify which is the oxidation step and which is the reduction step. Just to review that, the electrons are on the right here, so that means this must be the oxidation step. The electrons are on the left here, so this means this must be the reduction step. And then finally what I have to do is do whatever math I need to do to make sure that the electrons cancel out on both sides of the arrow when I then add up or recombine the half reactions. All right, so I do that, distribute through, cancel electrons, bring the 2 half reactions back together, and we're finished. So we'll work on a few more of these for practice next time in class. So we'll see you later.